Here's an example of torque applied by a motor and giving power information. So we have a motor that's applying 3 kilowatts of power that's spinning at 50 revolutions per second, and it's driving a shaft that has 2 different gears, one at A and one at B. At gear B, 200 kilowatts is removed, and at gear C, the last 1 kilowatt is removed. The shaft's diameter is 25 millimeters, and we need to find the maximum shear stress in AB and the maximum shear stress between B and C. We need to assume continuous and cohesive. It's in static equilibrium, and the weight of shaft is negligible. Alright, so the first thing is let's convert our power to torque, because we need to use torque in these shear stress calculations. So we are given that we're given a frequency of 50 revolutions per second. So we're going to use power equals 2 pi ft. So then solving for t, we have power over 2 pi f. So at C, or what the motor is applying, we have 3 times 10 to the third Newton meters per second, which is a watt. We're going to divide that by 2 pi, and we have 50 revolutions per second. So at C, we have a torque of 9.55 Newton meters. We can do the same thing for B, where we have 2 times 10 to the third Newton meters per second over 2 pi 50 revolutions per second. .37 Newton meters. And then at A, again, we have 1 times 10 to the third Newton meters per second divided by 2 pi times 50 revolutions per second, which is 3.18 Newton meters. So now what it really looks like is we have a shaft, and at C we have a torque applied. At B we have a torque applied, and at A we have the opposite. We have A and B in the opposite direction of C. And then we just found that this is 9.55. This is 6.37, and this is 3.18. Alright, so now if we do free body diagrams, so we can find the internal load seen between B and C and A and B, we can take our shaft, apply our load at C, and cut it off before we get to B, so then we have a torque applied in the opposite direction, TBC. So we know that TBC is equal to TC. So therefore our max shear stress between B and C is equal to the torque, BC, times C, the radius, over J. So we have 9.55 Newton meters times our radius, 0.0125 millimeters, or meters, sorry, over J, which is pi over 2 times the radius to the fourth, which is 3.11 megapascals. All right, then if we do our second one, if we take our shaft, apply our torque at C, apply our torque at B, and then cut it off before we get to A, so we know that the torque between A and B, we have TAB plus GC minus TB is equal to 0. So TAB is equal to TB minus TC, which is negative 3.18. So our tau max AB is equal to negative 3.18 times 0.0125, which is my radius of my shaft, times pi over 2 times 0.0125 to the fourth. So my maximum is 1.04 megapascals.